Here, we are asked to find the unit vector along the direction of the cross product of two other vectors. I would like to take the moment to reflect on what a unit vector is and perhaps why it could be useful. I'm not sure, but let's see. As always, I'm constrained to the two-dimensional space which I can function in. I don't think I have the artistic capacity to draw things in 3 dimensions that look nice. So we'll just stick to 2 dimensions. What is the unit vector of a normal vector? So this is just some vector, and let's call it W. What is its unit vector? Well, unit usually means 1. Usually means something that's standard. Probably that is going to be the case. I take this vector and I normalize it. By normalize it, I mean I bring it down to standard length. So I want you to think of a place where we can just focus on the direction of the vector rather than the length of the vector. For example, this is a vector. If I rotate it like this, I'll get another vector. If I rotate it like this, I can get a third vector. If I rotate it like that, I get a fourth vector. These are unit vectors. But not every vector is a unit vector. Usually have vectors that look like this. It's something that's stretched to the front, or something that's in the other direction, or whatever. So you have different types of vectors. And the way we can actually talk about their directions, and we can focus on what direction they're pointing at, is if we give them all the same length. So I want you to notice that for this other vector which I've introduced, I'll give it a very funny name, which is x. I can take this vector and I can scale it down to the unit vector. Perhaps let me use this. I think this is significant. So it's like I just cut it down, I shrink it down. And how do I shrink it down to the unit length? So this should be interesting. And we know that if we have a vector W, then this vector W probably has some norm. Norm is the length of the vector. And it is denoted as follows. Usually in two-dimensional space, it is the square root of each coordinate squared. So you would take, for example, first coordinate of W squared, and you take the second coordinate of W and square it. In 3 dimensions, it's an extension of the same idea. And here, in 2 dimensions, it's a very natural concept, I would say, because this is effectively just the Pythagorean theorem. So you have a displacement of W1 here and a displacement of W2 here. Well, not here. We're talking about the big vector. So displacement of W2 here and the displacement of W1 here. So you get the length. I would like to convince you that if we go on into 3 dimensions, you would have the same setup. But this would be a bit hard to argue for without having this video go over 30 minutes or something like that. But if we are in 3 dimensions, we would do the same thing. So we take the square root of all the components squared. This is the standard norm, you could say. There are other ways to measure the length of a vector, but this is the Euclidean norm, the normal one that should actually measure a normal distance. Normal in the sense that we're used to. Okay, so this is the norm. What happens if I divide the components of this vector by its length? So what happens if I have this vector and I divide it by its length? What happens to its original length? Let's see. And so if I do this, this is just the length, or the norm is just a scalar. So I can write W1 over W, W2 over W, and W3 over W. So this vector will be, let me call it with a small u, because this will be the unit vector. Why is it a unit vector? Because I now claim that the length, this was the original vector W, I claim that the length of the vector WU is going to be 1. Let's see. Well, proof. What is the proof here? It is very simple. I just compute the norm of WU. The norm of WU will be the square root of the squaring of each component in this vector. Just like this. I square this, I square this, and I square that. When I do this, it is very good. It is the same thing as squaring this upper part and this lower part, this upper part and this lower part, upper and lower part. And now I would like you to notice that I actually have this number, this norm of W as a constant. So I can factor it outside as in the denominator, I mean, of course. So this is W1, W2, W3. Remember, I'm adding them, and I'm taking a common factor of 1 over W squared. If this is too fast, then probably you should play this video on a half. Right? Okay, this wasn't funny. I apologize. We have this, and I can do something with this setup. And this something is that I can bring this even outside. So I can take this 1 over W squared and put it outside of the square root. But I need to take the square of it. So what I'm saying right now is that you can write this as that. When you write this as that, then the square cancels out with the square root, and you get 1 over W. And now it's really the moment of truth. Really it is. Because this is the norm of W, and this is the norm of W. You see, so this is so amazing. I'm so happy right now. Aren't you? So by dividing by the norm, I've effectively said, okay, I'll just divide by the norm so that when I multiply by the norm, I get 1 because they'll cancel out. Now, this red part is referring to the equivalence between this thing and that thing. They're exactly the same thing, right? If you take the components and you square each one of them under the square root, then you get the norm. So this unit vector actually has length 1. I hope this is not too abstract. I know we're using letters and not numbers, but you can test this out yourself with, let's say, 1, 2, 3 as numbers, and you will get the same result. So this is very strong. It turns out that if we take we have a vector, let's say like W, and we would like to find the unit vector, then we just divide. We just divide by its norm. Well, this makes sense. So the vector has some length. We divide by this length, we get 1. So now it has length 1. It's like if it has length 5, and I now divide by 5, so I get the vector of length 1. It won't get 0, but it will get the vector of length 1. So this is also a very layman's terms way of explaining it. But this is good. Now we can start doing our problem. So let's start doing our problem now. Remember, we would like to find the unit vector of what? Of the cross product of two vectors. So the first thing we need to do is to find the cross product of two vectors. And for here I have some set of notes that will help us. And this is how you find the cross product. You compute what is called the determinant. So I replace this u with these coordinates 7, -1, and 3. I replace this v with 2, 0, and -2. And I compute the matrix, not the matrix, it's a determinant. A determinant is not a matrix. And the way I compute a determinant is I choose a row or a column. Here, in this very specific case, we always choose this row. By choosing this row, I mean we would like to break this determinant down into smaller determinants. And we do this precisely as follows. So I write I write j, and I write k. Next to them, there will be smaller determinants, which we'll talk about in precisely one moment. Before we talk about them, we need to be careful with the signs. So here we have something that tells us about the sign that should be next to each term. Here our I is in the upper left corner, so it takes a positive sign, positive I, which is just I. As for j, it is right here, therefore it takes a minus, and finally for k it takes a plus. Now how do we find the smaller determinants that I've been talking about now? Well, it's not too difficult. You choose your entry, you eliminate the rows and columns in which your entry is in, and you take the remaining terms. So here I would just take -1, 3, 0, and -2. because these are the remaining ones. I do this again for j. Perhaps you could try to pause the video and do it. I get 7, 3, 2, minus 2. I do this one more time. I get 7 minus 1, 2, and 0. Now let us compute this very quickly. By compute, it means that I'm going to take a quick look at what the value should be. It should be 2, 20, and 2. 2. Well, this is going to be minus 20, because when I multiply it will give me 20. And then this will be 2. So I multiply this by the minus sign, I get 20 here, in case 2. Now I can write this even more compactly as follows. I write it as 2, 20, and 2. These vectors are unit vectors in, well, the standard unit vectors in certain directions. And by using these set of vectors, we're able to describe what our displacement is in each direction. So we go 2 steps in I, 20 steps in J, and 2 steps in the direction of A. So this is just a more compact way of writing it. So we write it like this, and here's what we do next. We find the unit vector. So to find the unit vector of u times v, which I'll call u times v unit, so with this small u, we would like to take the u times v vector, and we would like to divide it by its length, which is also called the norm. The norm of u times, did I say u times w? I hope I didn't. U times v. If I did that, that would be very bad. So this is good because we already have u times v. We just need to compute the norm of u times v. And as we've seen earlier, this is just going to be the square root of all the components squared. Well, each component squared. So 2 squared, 20 squared, and 2 squared. But don't forget to add them up. This is going to give you a number. This number is going to be the square root of 408. And if this number is going to be the square root of 408, well, I think it is easy. I don't need to look it up, right? 20 squared is 400, and this is 4, this is 4. Anyway, I do this now, and if I'm successful with these steps, then the answer should be to take u times v which is precisely this set of coordinates, and multiply it by, well, divided by the norm. And the norm is what? It is square root of 408. So I place it in for the square root. Maybe I'll place everything up just for the sake of niceness. And this should be your answer. You could, take an extra step and distribute this inside, but I don't think it is wise or time effective to do so. I think for this exercise, this answer should be more than enough.